Okay, this is a follow-up video for the question 10 of Crescent Girls 2014 Pure Physics paper. Okay, this question is very interesting. Now, most students may, at first glance, think that this is a very straightforward question. It is about stable equilibrium and it's about the position of the CG must be within the base. Now, the thing about this is that if you choose option D because you think that this is my base, and if my CG is within the base, it is going to give me stable equilibrium, just like what the textbook is saying, then you will realize that you get the wrong answer. Or if you try to work out the moment, you find that it actually contradicts with what the textbook is saying. Now the thing about this system is that it actually consists of two parts. This orange part whereby you have the aeroplane and the lever and you have the weight, and this base, this stand here. Now what the question is asking is that, what the question is highlighting is that the toy, which is referring to this orange thing, is the subject of the question. Okay, it's not about this base. It's not about this stand. So the base here is the base of the stand. It is not the base of this orange part here. The orange part here has no base because it is resting on a point pivot. So if you use the theory given in the book that says the CG is inside the base, it will give you stable equilibrium, you cannot apply that here. Because the subject of the question is this orange lever, and this orange lever is resting on a point pivot, there is no base here. Okay, the base here is this base here refers to the base of this stand. So if you say that, okay, this CG here, the center of gravity, okay, is of this entire thing, the base, the stand plus this orange part, then yes, it is stable in this point. Okay, but the question is actually referring to just the toy, just the orange part. So there is no base here. You cannot use that rule of thumb that the CG is within the base and it will give you stable equilibrium. It just cannot be used here. So how would you approach this question? You can actually do it by elimination. So if you look at option D, let's start with option D since we have been talking about it. Okay, if now the CG of the orange part is here, somewhere here, in between the weight and the stand and the pivot, what happened here is that, so the weight of the orange part will be here. There's the line of action of the weight. It's just an extension of the vector. Then you notice that there will be a perpendicular distance between the line of action and the pivot, and so it means that the weight of the orange part here will cause a clockwise moment. So what does it mean? It means that this orange part cannot even be balanced about this pivot if the CG is here. Because if the CG is here, there will be a constant clockwise moment acting on the host on this orange part, and the orange part will simply be toppled. It is kind of like if you are balancing your pen here, the weight, because the CG of this pen is somewhere here, the weight of this pen is going to cause a constant clockwise moment. So if I release my hand here, what happens? It simply cannot balance. It will just topple. Simple as that. So similarly, if you look at option A says that the CG of the orange part is inside the weight. So let's erase this. Now if the CG is within the weight, what happens? There will be downward force here. There is a perpendicular distance here. So this weight is going to cause a clockwise moment. Okay, and it simply says that the orange part cannot be balanced about the pivot here if the CG is here. Simple as that. So you know that A and D is out. So you're only left with B and C. Now if you look at B says that the weight of my orange part is here. So I think by now you should be like instinctive thing. If now the weight is acting at the pivot, there is going to be no moment, right? Because you don't have any perpendicular distance, so the moment is 0. So when the net moment is 0, it simply indicates that this orange part is going to be balanced on the pivot. But is that enough? So if you look at the question context, it says that the toy is going to be balanced about the pivot, and if the toy is now slightly disturbed, it's going to return to its original position. Now, will that happen if your CG is at the pivot? Okay, will that happen? Now, there's actually two ways of showing you. One is mathematical, one is through a demonstration. So I'm going to show you through a demonstration because it is very simple. Now, imagine now this finger here is a rod, perfectly round rod, and you are going to balance the pencil here. So when the pen is balanced on my finger, what is actually happening is that the CG of the pencil is now exactly at the pivot point, and that is why there is no net moment acting on the pen, and so the whole thing is balanced. And now if I slightly disturb it, what happened? Okay, it's still going to return to its original position, and that is because my finger is not a perfectly round finger, right? It has some flatness here. So if I disturb it more, what will happen? It's going to topple. Now, I want you to exaggerate this case to the edge of a ruler. Similarly, by carefully positioning your pen, you can achieve equilibrium. Okay, just that now it is even more difficult. It is difficult because a slight disturbance is going to cause your pencil to be imbalanced, right? But if you do it long enough and careful enough, you can find the sweet spot whereby the CG of the pen is exactly at the pivot, and the pen is going to be balanced. But you also know that just by slightly disturbing this pen, the pen is going to topple. So it proves that if your CG is exactly at the pivot, yes, it's going to be balanced at the pivot, but it is not stable. A slight disturbance will cause the whole thing to topple. Okay, so now I demonstrated to you that B cannot be the answer. Then of course you can say that, okay, so through elimination, you know that C is the answer. But for the completeness of this go through, we will prove that C is the answer. But before going into option C, I would like to challenge you to give me a mathematical and scientific proof, or mathematical proof. Why would option B give you an unstable equilibrium? Okay, I challenge you. Okay, now let us move on to option C. Now option C says that your CG is now below the pivot. And if we are to analyze this, we have to mathematically prove that no matter how I disturb the system, it's going to return to its original position. Now to do that, you need to have one additional concept here. This additional concept is about the position of the CG. Now the position of the CG is not going to change if you disturb it. The relative position of the CG is not going to change. What I mean by relative position. So let's say I have an irregular object. Okay. Let's say this irregular object is a triangle. Okay. For the sake of this explanation, let's use a regular triangle. Let's say the CG is here. At the midpoint of the base, perpendicular to it, 5 cm. Now, no matter how I orientate the object, let's say I shift it this way, I flip it over, the position of the CG in relative to the base here is always going to be perpendicular 5 cm, midpoint. It's going to be midpoint, perpendicular 5 cm. It's always going to be the same, no matter how I orientate my object. So similarly, if now I have, let's analyze this. If now the original position of this lever, which is the orange part, let's say now my CG is going to be right at the pivot but below it about 5 cm. So what I'm saying is that my CG of my orange part is going to be here, perpendicular down 5 cm. Okay, so remember this, the relative position of my CG to my lever is going to be constant. Okay, it's always going to be like that, no matter how I orientate the lever or the orange part. So now if I give it a slight disturbance, okay, let's give it a slight disturbance. Okay, everything, I must keep everything the same. So let's use dotted line as a reference. Okay, so now let us try tilting it to the right. So let's tilt it to the right. Okay, I tilt it a little bit. Now, the relative position of the CG is not going to change, right? So it is still going to be at this pivot, perpendicular to the lever, 5 cm. So it's around here, 5 cm. Right? So what will happen is that if this is the CG, there will be a weight pointing down. And if now I draw the line of action, the pivot is going to be here, right? Okay, let me zoom in now. Okay, so the pivot is going to be here, yeah, and the line of action is here, so there is going to be a perpendicular distance, meaning that the weight here is going to generate a what's this direction? So the weight here is going to generate a counterclockwise moment, and therefore your lever is actually going to be moving back to its original position. Yeah, okay, so now we have proved that if my lever is tilting this way, the CG is going to generate a counterclockwise moment and return it to the original position. So now let us try to tilt it another way. So now I'm going to tilt it another way. So let's try to tilt it. So now I will tilt it this way. Okay, so the same. I am going to locate my CG first. So it's going to be from this point, perpendicular to it, 5 cm. This 5 cm is arbitrary. It can be 3 cm, can be 100 cm, can be any cm. Okay, so again, if you look here, okay, then I draw my weight factor, and then I'm going to draw my line of action. So you can see that there is a perpendicular distance between the line of action, okay, there is a perpendicular distance between the line of action to my pivot, meaning that the weight here is going to cause a clockwise moment on the lever, and this clockwise moment is going to return this lever to this position. And so now we have proven mathematically and scientifically that by positioning the CG below the pivot, you will actually get a stable equilibrium whereby the toy, when tilted slightly, is not going to topple and is going to return to its original position. Okay, so I know this is a long explanation, but this is a really interesting question. Okay.